Hello, chemistry students. I wanted to go through and do a quick video about molecular structure or VSEPR, VSEPR theory, and that's how we determine the shapes of molecules. So you've been drawing those Lewis structures, and we're going to take those Lewis structures and use them to predict the shapes of molecules. Alright, so what VSEPR theory says, or what it stands for first off, is valence shell electron pair repulsion theory. And basically what this says is that pairs of electrons, whether they're in bonds or if they're lone pairs, are going to orient themselves around a central atom in a way such that minimizes the repulsive forces. Remember, electrons are negatively charged, so a bond would repel another bond, or a lone pair would repel a bond, because they all consist of electrons, so they are all negatively charged. They would push each other away, and that helps us determine, for example, that if this was your central atom, then there would be these two bonds would orient themselves exactly 180 degrees away from each other to minimize the repulsions. Alright, so when you're analyzing for VSEPR theory, there are two types of electron pairs. There are bonding pairs and there are lone pairs. And the lone pairs take up more space and repel more strongly than the bonding pairs, and that's going to be important when we determine the bond angle, because when there's a lone pair on another side of the molecule, then it actually squeezes this bond angle in a little bit closer together. We'll talk about that more in just a moment. Okay, so when you're determining molecular shape, you draw the Lewis diagram, you count up the electron pairs on the central atom, and double and triple bonds only count one time when you're counting for determining the molecular shape, and I'll try to explain that more fully in just a moment as we go through some examples. Okay, the shape is determined then by comparing the number of bonding pairs to the number of lone pairs, or the number of bonds. So when you're counting the number of bonds, if there's a double or triple bond, that double or triple bond only counts once as a bonding pair. The lone pairs, that would be two dots, lone pair of electrons on the central atom, and sometimes you have central atoms that have more than one lone pair, usually two, sometimes three, but usually one or two lone pairs is common, and more than that is less common. Alright, so we have a linear molecule here, the BH2, and then we have a trigonal planar molecule, the BF3. Now, SO2, if you draw the Lewis structure for that, you end up getting... Alright, so I took a moment to draw the Lewis structure for SO2, and to satisfy the octet for sulfur, you end up having to... to satisfy the octet for the oxygens, you end up having to share a couple more of the sulfur's electrons, so you actually violate the octet rule for sulfur. But once you get to the third period, sometimes you do actually, it's okay to go over the octet rule for that. So I'm helping you out with this to get you to the Lewis structure, which is going to show you this. Now, the central atom in this molecule is the sulfur atom. The central atom is easy to locate. It's the one that's in the middle. And if you look around this, it has two bonds. Remember, double bonds and triple bonds only count once. So we count each double bond once. We have two bonds and one lone pair of electrons. Here's the lone pair of electrons. So once we're able to identify that, then we can look at the shape, and we can see that is going to give us a bent shape, because the lone pair would fill in here, and then the actual shape of the molecule is the bend that you see here. Now, methane is the name of this molecule. It's going to have a tetrahedral shape, and then ammonia has 3 bonds and 1 lone pair. It's got a trigonal pyramid shape. Water is a bent molecule. And then we have some more exotic shapes here, the trigonal bipyramid trigonal, because it has 3 in the equatorial position and then 2 in the axial position. So this thing looks sort of like a space station where it would spin around. And just to draw attention to the fact that we said that that lone pair could squeeze the other bonds together. Normally the bond angle for a tetrahedral shape would be 109.5. And you'll just have to trust the people that know how to do three-dimensional geometry that that's the angle that these bonds actually come out to be. I'll show you in 3 dimensions what that looks like in just a moment. But when you have a trigonal pyramid, which has the same electron geometry, as far as there's 4 places where there are regions of electrons around the central atom, so 1, 2, 3, 4. That lone pair is more repulsive, so it pushes the bonds closer together, so the bond angle from fluorine to phosphorus to fluorine is 170 degrees instead of 109.5 like it would be for methane. Here's another one, carbon dioxide, that's pretty common. That ends up being linear because around the central atom there are 2 double bonds, so 2 bonding domains and 0 lone pairs. Now, let's go over here and look at a simulation I've got pulled up for molecular shapes. And once you draw the Lewis structure, you could actually come over to this if you wanted to. And if you add, you can add bonds to the molecules. And what you can see, let me take one off. So if there's a central atom and there's an atom bonded to that central atom, there's no way for this to be anything but linear. Okay, if you add another bond, well, it's still linear, no matter how you move it around. And things starting to get interesting. Let's take a bond off and put a lone pair on. That would be a really uncommon arrangement. In fact, I don't think I can think of an example of something that actually looks like this in real life, where there's only 1 bond and 1 lone pair. But it's still a linear molecule because the bond angle or the molecular shape is determined by where the molecules are at, not by where the lone pairs are at, even though the lone pairs influence the shape. All right, so let's add another bond. Take off a lone pair for right now. Too far. Okay, so once we get into more than 2 bonds, then we actually get some interesting shapes. So this is called a trigonal planar shape, and by the way, it's called trigonal planar because all of the atoms are in a flat plane with each other. So geometrically you can kind of look at that and see that, you know, this is a flat surface. There's a plane that would go through all of these. Now, right now the molecule geometry and the electron geometry match. Now let me show you what happens if I do 2 bonds and a lone pair. So we still have the electron geometry. It's still trigonal planar because these are all still in a plane with each other. So a flat surface would go through all of the bonds and the lone pair. However, the geometry of the molecule is bent because there are 2 bonds and 1 lone pair. Alright, let's note that if I replace one of the bonds with like a triple bond or something, the molecule geometry is still bent. So it doesn't matter if it's a single, double, or triple bond. Each bonding domain only influences the shape as though it's 1 bond. All right, let's take that off. And well, this is also pretty rare, but notice that if this happens, you still have the trigonal planar electron geometry, and the shape of the molecule, though, is linear because there's only two atoms in this molecule, so the only shape that the atoms can make is a straight line, so it's linear. Alright, let's get the lone pairs off of there. Okay, let's add this fourth, and that makes this tetrahedron. Okay, and you can see that this sort of looks like I guess it almost looks like a pyramid if you connected the lines and everything to each other. It's called a tetrahedron because if you connected all the endpoints to each other, they make a four-sided figure, so that's where the tetra part comes from. Okay, right now the electron geometry and the molecular geometry match. That'll always be true when the number of bonds is, or basically when there are no lone pairs, then the molecule and the electron geometry will match. Now, let's take off a bond, add a lone pair. That changes the shape to something that we call trigonal pyramidal. And the reason why it's called a trigonal pyramid is, see how it kind of looks like a pyramid here, and it's trigonal because it's a three-sided pyramid. I'll spin that around so you can kind of see some of the three-dimensional stuff going on with it there. Okay, it's a very common molecule shape. And then also let's remove a bond and throw another lone pair on there. This you'll recognize as being very similar to a water molecule. It's got two bonds and two lone pairs, and the geometry of the molecule is bent. See the bend here? So some people, when they draw this, they draw it like so, and they're like, oh, that's a linear molecule. Well, no, if you look at it in 3 dimensions, those lone pairs cause it to be bent. So it still has the tetrahedral electron geometry, though. All right, now, I want to make a point here. Let's show the bond angle. Oh, they don't have the real bond angle on here. Okay, so they put the ideal bond angle. That's fine. Let's go over here, and I think I have an option to do some real molecules. By the way, if you're interested in doing more stuff, there are a lot of other shapes that come about. You can go up to 6 bonding domains and get some other funky shapes. I'm going to show you some real molecules real quick. Okay, so in a real molecule, those lone pairs push the bond angles together. Remember, this is a bent molecule, the water molecule is, and those lone pairs repel more than bonding pairs, so instead of this bond angle being 109.5, it's a little bit less, 104.5. You don't have to memorize that it's 104.5, but you do need to know that it would be less. Okay, let's check out carbon dioxide. There it is, double bond, so 2 bonding domains, no lone pairs. Alright, there's the sulfur dioxide that we looked at earlier. Notice that this bond angle, if you divide it up 360 degrees by 3, should be 120. The lone pair pushes the others closer together, pushes the bonds closer together. So the bond angle is slightly less than 120 degrees. Okay, there's the BF3. Boron violates the octet rule here if you try to draw the lowest structure, and so you end up, boron is satisfied, which is 6 electrons in its octet, and the bond angles there are 120. Let's take a look. There's something crazy. Check that out. Anyways, let's see. Yep, there's a T-shaped molecule. That's cool. We won't go up to those. We only do 4 electron domains in this class. Okay, here's a really common molecule, is the ammonia molecule. Notice the bond angles there slightly less than 109.5, and that's because of this lone pair up here. Okay, trigonal pyramid there, tetrahedral electron geometry. Methane, bond angles are the same all the way around because they're all bonds. And I think I'll stop there because the rest of them are pretty exotic. Hope this helps you with molecular geometry, and thanks for watching.